So once again, good afternoon, everyone. And I'll be speaking on spectral estimation based on compressibility. I'm currently a postdoctoral researcher at the Czech Academy of Sciences. And this work was done in collaboration with Dr. Nitin Nagraj, who is an associate professor at National Institute of Advanced Studies in Bangalore, and he's also present in the conference here. So starting with that, let me begin with the tale of two kingdoms. So these are the two kingdoms which are of utmost importance in the field of signal analysis or time series analysis. And on the left, you can see the kingdom led by Fourier. So he was the person who gave the idea of Fourier analysis and Fourier transforms and so on. And basically, what he said was that you could take your time domain signal to the frequency domain signal and analyze your signals in the Fourier domain, which would help you to get some information about the signals, which is not possible in the time domain, right? And so this was the idea of spectral analysis, and there are many other ideas related, which were, came up along with Fourier's idea were about the linear filters, about wavelets, time frequency analysis. However, all things in this kingdom, work in a linear fashion. So the data is linear, the operators are linear, and so on. And the second kingdom, as you can see, is the kingdom led by Shannon. And he gave the idea of Shannon entropy, which is, with which the field of information theory started. And he said that you could, given any random variable, you can get the information content associated with that random variable based on Shannon entropy. So there are also related ideas of mutual information and channel capacity, and the field of data compression is actually very, very closely tied up to this field of information theory, and it is basically about compressing data. And Shannon entropy also gives the bounds on the best possible data compression for any given variable or time series and so on. However, all things in this second kingdom are probabilistic, right? So, most of you would have used one or more tools from these two kingdoms. So with that, the thing is that what you saw now is that you can either analyze your signal based on Fourier ideas, or you can analyze based on information theoretic ideas, but there's no sort of connection between the two. So we were, asking this question that can we do the spectral analysis, let's say, based on information content in the signals, right? So the need for the signal analysis tool that can bridge the two kingdoms, and so we come up in this work with this idea of a compression spectrum, which can capture information content at different frequencies or scales. So how do we do it? We use this effort to compress compression algorithm, and it is basically, this measure is a measure of compression complexity, and it can help to capture the complexity associated with any given time series, or a sequence of symbols. So how does this work? So very literally, this effort to compress measures the effort required to compress an input sequence using compression based on recursive pair substitutions. And I will show this to you how it works, like using an example. So for example, if you have the sequence 0, 1, 1, 0, 1, 0, 1, 1, right? So in this sequence, which is the pair that occurs most frequently, you can see that it is 0, 1. Right? So you can replace the 0, 1 with a 2 in the next iteration, and you will get something like 2, 1, 2, 2, 1, right? And in this iteration, now 2, 1 occurs most frequently. So in this iteration, we can replace 2, 1 with a 3, and we get like a 3, 2, 3. And now none of the pairs are, both the pairs are basically equally likely, so we replace the first one. And we get a 4, 3, and we stop at 5. So ETC is counting how many steps are required for this kind of iterative method to reach either a constant single number or a constant sequence. Let's say all your numbers in the last step become 5, so 5, 5, 5, something like that. And so basically, ETC is calculated as the number of steps in the algorithm, and the normalized ETC is the number of steps divided by the length of the original sequence minus 1. So with that, let's look at some examples to understand how ETC works. And if you have like a sequence 1, 1, 1, 1, there's no more steps required to compress it further. So the ETC and the normalized ETC also is 0. But if we have like periodic sequences like 1, 2, 1, 2, so on, for the 1, 2, 1, 2, we'll need 1 step to compress it, and the normalized ETC would be 0.2. Right? So as you can see, for periodic sequences, we require very few steps, and the normalized ETC is also low. But for random or all distinct kind of sequences, we require more number of steps, and all these steps are actually equal to the length of the original sequence minus 1, and the normalized ETC is 1. So once again, periodic sequences have low ETC values, and random and structural less sequences have high normalized ETC values. So with that, ETC has been used in a number of applications in complexity estimation from time series, designing methods for causal inference, and it has been shown to be better than Shannon entropy and levels of complexity for characterizing the complexity of short sequences, also noisy sequences. And it is found to have like a dimension-like interpretation. So if you're more interested in that, like box counting dimension-like interpretation. So if you're more interested in that, you can check this paper below on time reversibility, causality, and compression complexity. And so coming to the idea that we introduce in this work, right, it's called a compression spectrum. And basically, you see how in the ETC algorithm, the length of the sequence always reduces at each step, right? So this is owing to a substitution at each step. And what you can do is you can record the compression ratio at each scale. So basically, for example, in the first step, right, so the length of the pattern was actually 2. So that can be thought of as the scale. Right? So you can calculate the compression ratio as the length before substitution upon the length after substitution. So during iterations, we may return to an earlier scale for pair substitution. So for example, even when we go down, we may encounter some cases where we return to a pair of length 2, right? So we can accumulate all these compression ratios, and we can sum up the log of these compression ratios. And ultimately, we can plot the log of the compression ratio versus the scale or the pattern length. So that's how we get the compression spectrum. And so if we have like sequences like this, right, 1, 2, 1, 2, so on. So we will get like the maximum value of the compression ratio will be at the scale of 2. And that will be the only scale at which we will get the compression spectrum, because the information is all at that, all in that pattern 1, 2, 1, 2. So if we move further ahead, right, and we have patterns like this, 1, 2, 3, 4, 1, 2, 3, 4, and so on. So in this case, we will have like compression ratio at scale 2 as well as scale 4. So with that, moving to period 8, you can notice that we will have peaks at 2, 4, and 8. And if we go to a sinusoid, in this case, what will happen is that we will have like the highest value of scale that we will observe in the compression spectrum will correspond to the period of the sinusoid. So it's basically at the scale 20, as you can see it, right? And there will be also some information at smaller scales, because there is a repetition at smaller scales. So we will get some values of the compression spectrum on those scales. As you can see that the signal repeats even at, there's some information also at the smaller scales, let's say 2, 3, and so on. So, however, if we use the same sinusoid and we use a different sampling frequency, right, and we basically get these samples corresponding to the peaks of the sinusoid, right? So in this case, we will see that our signal actually has less information content, and we will get like a compression spectrum only at scale 2 and 4. So basically, this was some differences that you observed in the compression spectrum with some periodic examples. Now moving on to the case of chaotic time series versus uniform random time series. what will happen is that if we have, like, for example, like a chaotic logistic map, we get like a broader compression spectrum. So there are more non-zero values compared to a random compression spectrum because there's not enough information actually at at the higher scales, and at the lower scales, the information that we get is purely due to chance. So we can define like also like the bandwidth of the compression spectrum, which are like the number of non-zero values in the compression spectrum. And if we compare like what happens to the compression spectrum as we increase the amount of chaos, right? Like, for example, if we use logistic map and we vary this parameter A in the logistic map, we will get like, first we have Lyapunov exponent, which is less than 0, and then it becomes chaotic. So in accordance, in the compressibility spectrum, we will see that initially the values are actually close to 0, and then they become high in case of weak chaos, and then they drop down again in case of very high chaos. So probably the signal is becoming like more random-like, and so this is happening. So now moving on to the example taken from real world, we took some RR tachogram data. So these were like heartbeat intervals recorded from young and young healthy and elderly healthy human subjects. And we looked at, this data was taken from PhysioNet, and we basically analyzed these data sets of young and healthy patients based on the compressibility spectrum. And I show just the result of one patient, and you can see here that this is the compressibility spectrum for the young adult. This is for the old adult. And we can basically do a linear fit to the bandwidth in case of the young adult, as you can see, right? And we get some slope minus 0.343. And for the old as well, we can fit we can fit, but of course it's not a proper fit because we can see that it's not really like, there's no linear line, a line that we can fit to the log-log plot of compression ratio versus scale. And what is so special about the slope of minus 0.343, right, that we get for the young adults? So we also did a similar thing for 1/f noise. And we see that the slope is actually very close to what we got for the young adults. And I mean, of course, here the fit is very, very proper because it's 1/f noise and it's fractal-like. But the slope being close to the young adult slope being close to fractal noise actually shows that it exhibits some fractal-like properties, which has already been shown in literature, like 1/f-like noise-like properties, to be very precise. And so that's something interesting, and we plan to do more such experiments on this data. And so finally, to conclude, so compression spectrum is a simple and intuitive tool for simultaneous spectral analysis and information content at various scales. And one important thing is that it is very robust to nonlinearity and non-stationarity of the data. So even if the data is short-term stationary, we can use this tool. And some interesting things that we notice is that weak chaos has high bandwidth. RR tachogram of young, healthy adults has similar bandwidth to compression spectrum of 1/f noise. And this is just a very preliminary work along this direction. And as Professor Nilima said in the morning, it's just a perspective on, what perspective could be taken going forward. So thank you.
Thank you, Aditi. Thank you very much.
And the code is also available if anyone is interested to use.
Yeah, the floor is open to questions.
I have a couple of questions, but I'll give you the simple one. You said that your method is better than Limpelzev and Shannon. What do you mean by better?
So basically, this was with respect to the, if you do complexity estimation of time series, right? And you just want to characterize how much structure the time series has or not, or a symbolic sequence has or not. What we have found is that if you use Shannon entropy on short sequences or noisy sequences, there are problems that come up when you estimate the probability distributions, right, on short-term data. Compared to that, when we apply ETC on such kind of time series like short length or noisy, we are able to estimate the complexity of time series much more robustly. Limpelzev also, but in some cases we also get better complexity than Limpelzev. Yeah. Thank you.
Aditi, I was wondering, have you analyzed intermittent signals?
Sorry, I can't. Oh, yeah, sorry, yeah.
Have you looked at intermittency?
No. So can you tell a bit more elaborately what that means?
Well, you know, in the logistic maps, a signal which
I
is
see.
intermittent, which would have a very long, long sequences and a lot of structure.
Okay. Okay, we'll definitely check that out. Thank you.
I have a question. So when this is on, I'm asking up here. Yeah.
Oh, yeah,
Yeah.
sure.
So this is, continuation to what you was asking about. See, when you say Shannon entropy and Lempel-Ziv complexity, they are two different measures in some sense. So whereas if you take the, kind of derivative measures for Shannon entropy, not derivative is the right term, but it's family of terms like approximate entropy, sample
Right.
entropy.
Yeah,
And
yeah,
the particularly very effective version of it called permutation entropy, which does look into this probabilistic characteristics and work for very, good signal to noise ratios.
Right.
So can you make a remark against whatever you have done against, say, permutation entropy, for example?
Yeah, so first of all, like permutation and entropy comparison, we have not done with effort to compress.
Yeah.
Because permutation entropy is just like converting your sequence to ordinal patterns and then doing Shannon entropy, right? Which we can also do with ETC, for example.
But that's something you do even in Lempel-Ziv, right? You put a threshold and convert to ones and zeros and then go for some kind of accounting algorithm. and
That's
so forth.
basically binning. But
Yeah.
when you use permutation entropy, right, you use ordinal patterns. You
Right,
also
yeah.
use like a geometric or a topological interpretation, right?
That's right.
So
Yeah.
that interpretation can also be brought in for effort to compress. So you can do that and then you can do effort to compress. But that's one thing. But considering your questions about approximate entropy and symbolic entropy and so on, there's some work which has been done by Dr. Nitin, whom I collaborate with, and
Yeah.
he has published some papers with his students on, comparing how the three work and this paper called Three Perspectives on Complexity, for
Right,
example.
right, yeah.
So we could refer you to that. But in many cases, we see that ETC actually does work better.
Okay. Thank you so much.
Thank you.